In this example, we're going to start to talk about how we solve equations that have radicals in them. We're going to begin by reviewing our old solving strategies. In part A, how do you solve the equation r plus 2 equals 8? Well, to solve the equation r plus 2 equals 8, the first thing we would do is to subtract 2 from both sides of the equation. Notice that the question wasn't solve the equation, but how do you solve the equation? Well, because it was r plus 2, we subtracted 2. The reason we decided to subtract 2 is because when we have that 2 minus 2 on the left side of the equation, they cancel out. And on the left side of the equation, we get simply r equals. In this case, we end up with r equals 6, because 8 minus 2 is 6. But the focus of what we're looking at is how we solve the equation. Because we had plus 2, we subtracted 2. In part B, the question is, how do we solve the equation m divided by 7 equals 3? Well, because right now we are dividing the m by 7, to solve that we will multiply by 7. Just to emphasize, we'll multiply both sides of the equation by 7, but the reason we picked 7 and we multiplied by 7 is that is the opposite of what was being done. We originally were dividing by 7, so we multiplied by 7. And that action of both dividing and multiplying by 7 cancels each other out. And what we're left with is a simple m on the left side of the equation. And on the right side of the equation, 3 times 7 is 21. But again, the focus is not on what's the solution, but how do we solve this? In part A, when we originally were adding by a number, the way we solved was to do the opposite. We subtracted by that number. In part B, when we were dividing by 7, we multiplied by 7. We do basically the opposite of what's presented. More precisely, we do the inverse of what's presented. Opposites can sometimes be tricky because opposites often refer to negative numbers, and we're not always doing negative numbers or subtraction. But we're doing the opposite operation, or more precisely, the inverse operation. The inverse of adding is subtracting. The inverse of multiplying is dividing. In part C, what is the general technique we've learned so far for algebraically solving equations? Is to always apply the inverse operation to what is happening in the equation. So that brings us to part D. We want to solve an equation that has a square root in it, specifically the square root of the quantity y minus 4 equals 7. The complication here is that it feels like the inverse of taking the square root of something should be squaring it. If I start with the number 25 and I take its square root, I would get 5. And if I then square it, I get back to the 25, so that squaring and square rooting kind of cancel each other out. The problem that you will discover later on in the future in your mathematics studies is that they're not perfect inverses. They don't perfectly cancel each other out. So we will apply that idea, though, that because we have a square root here, we will square both sides of the equation, but we'll talk about in a second what complications this can introduce. So we have the square root of y minus 4 equals 7. I'm going to square both sides of the equation to basically cancel out that square root. The square root being squared, those do cancel out, and we are left with y minus 4. And on the right side of the equation, 7 squared is 49. Now that we have gotten rid of the radical from our equation, this is back to a regular linear equation. Y minus 4 equals 49, so we'll add 4 to both sides of the equation, and we get y equals 53. Now, because squaring and taking the square root of something is not a perfect inverse relationship, we do always have to formally check our solutions. Anytime we come up with a solution to a radical equation, we need to make sure it actually does work in the original equation. So to check this, we will put 53 back in for the y in the original equation. So the square root of y minus 4 equals 7 becomes the square root of 53 minus 4 equals 7. And remember, in this check, it's basically a question. Are these actually equal? Does this really work out? Well, 53 minus 4 is 49. And the square root of 49 is equal to 7. So we have verified that 53 is actually a solution for this equation, so we'll quickly write that down. So in part E, the general technique for algebraically solving equations that contain radicals is going to be this process. The first step is to isolate a radical. Before you go ahead and square to cancel out a radical, you have to make sure a radical is by itself on one side of the equation. So step 1 is to isolate a radical on one side of the equation. Once you have that radical isolated, you're going to have to use a power to cancel out the radical. Now we've just done a square root, so we squared. But if this had been a third root, we would have cubed. Or a fourth root, we would have raised both sides to the fourth power. So you're going to use a power, but you have to match the power to the index of the radical. So we'll raise both sides of the equation to a power that cancels out the radical. Again, your index and your exponent have to match to cancel the radical. Now the third step didn't occur here, but it could potentially occur down the road. If after raising both sides to that power, there is still a radical left in your equation, you need to repeat the first two steps, isolate that remaining radical, and use a power again to cancel out that remaining radical. Step 4. Once the equation is clear of all radicals, solve it like you would using all your other strategies. And finally, because this is a radical equation, you must check any and all solutions that you have come up with. When we have equations that have solutions that won't check, these are called extraneous solutions, and you'll potentially see that in a future video. It is important to note, if you come up with more than one potential solution for your equation, checking a single one of those solutions does not check all of them. Sometimes you could come up with 3 potential solutions, and maybe one of them will check, maybe both of them will check, and maybe all 3 of them will check. So you always need to check each solution individually.